Last time we began the discussion of discrete time processing of continuous time signals. And as a reminder, let me review the basic notion. The idea was that we convert from a continuous time signal to a sequence through an operation which I represent as a continuous to discrete time converter, and then that sequence is used as the input to an appropriate discrete time system, and after appropriate discrete time processing, that sequence is converted back to a continuous time signal through an operation which I label as a discrete to continuous time converter. Now, in the lecture last time, we carried out some analysis which related for us the spectra in the first step of this operation, namely in the transformation from a continuous time signal to a sequence. And let me, by the way, draw your attention to the fact that in the real world, this operation is essentially implemented by what you would typically label as an analog to digital converter if, in fact, the discrete time processing is being done digitally. Now, it's important to emphasize that it's not exactly what an analog to digital converter does, but in some sense at least, you should think of this mapping from continuous time to discrete time in very much the same way that one would think of an analog to digital converter. And the mapping back then corresponds in some sense to what would happen with a digital to analog converter. Well, let me review what is involved in the mapping from the continuous time signal to the sequence. And let me stress again that this operation is basically, in the continuous to discrete time conversion, a two-step process. In the first part of the process, the continuous time signal is modulated with an impulse train where the period of the impulse train is capital T. And so we have a continuous time impulse train signal which captures the samples of the original continuous time signal. That impulse train is then put through an operation which essentially relabels the samples so that the sample values, the impulse areas, are relabeled as sequence values, and the result of that conversion is then the sequence x of n. So the overall process then is a sampling process followed by what is simply, in this box, a relabeling process. And although, as I indicated just a minute ago, that is essentially what an analog to digital converter does, an analog to digital converter doesn't necessarily carry it out in those two steps, but particularly in terms of carrying through an analysis, thinking of it as a two-step process is particularly convenient. Now, we talked last time about what this mapping from continuous time to discrete time means both in the time domain and in terms of the spectra. And in particular, in the time domain, we begin with the continuous time signal, which is then sampled with an impulse train and converted to a sequence by simply generating a sequence whose values are the areas of the impulses. And I stress the fact that what this corresponds to essentially is a normalization of the time axis, essentially by dividing the time axis by capital T. In the frequency domain, then, we had the spectrum of the original signal, which, because of the sampling process, is replicated at multiples, integer multiples of the sampling frequency omega sub s, or 2 pi over capital T. And then in converting the impulses to a sequence, we are essentially normalizing the frequency axis so that the frequency 2 pi over capital T gets relabeled as 2 pi, and the resulting discrete time spectrum looks like I indicate here, which really is nothing more than a frequency scaling corresponding to the associated time scaling. So the mapping from the impulse train spectrum to the discrete time spectrum corresponds to a mapping specified by capital omega equal to small omega times capital T. And equivalently, it's the frequency 2 pi over capital T, which is, of course, the sampling frequency, which gets normalized to the frequency 2 pi. And so in the frequency domain, there is a frequency normalization associated with the fact that corresponding to this spectrum is a time sequence, or a discrete time sequence, as I showed previously, and the discrete time sequence is related to the original continuous time signal through a time normalization. In other words, these sequence values are simply samples of the continuous time signal with the time axis renormalized. Now, what we want to consider, this is the conversion from continuous time to discrete time. What we want to consider now is the overall system which implements not just the conversion, but filtering and then coming back out of the conversion back to continuous time. So let's look at the overall system. And the overall system, of course, as I've stressed several times in the past, consists of first the sampling process, conversion to an impulse train, and the impulse train converted to a sequence. That sequence is then processed through our discrete time filter, and after the discrete time processing, the result of that is converted back to an impulse train. So this resulting process sequence is then converted back to an impulse train, and then finally we carry out the desampling process by simply using a low-pass filter associated with a cutoff associated with the sampling frequency that we used. Now, typically in a system like that, which implements discrete time processing of continuous time signals, we need to ensure in one way or another that the bandwidth of the input is sufficiently limited so that we avoid aliasing. One way to do that is to force it in one way or another, or simply know that our signal satisfies the bandwidth constraint. Although a fairly typical thing to do, in addition to the sampling process, is to include what is referred to as an anti-aliasing filter. In other words, this is a filter that would band limit the input at least half the sampling frequency, so that we are guaranteed then that there is no aliasing that's carried out in this process. And it's important to stress that in this kind of processing, discrete time processing of continuous time signals, except in certain special situations, it's very important to avoid aliasing, because we're going to want to do a reconstruction after we do the sampling and processing. Okay, now this is the sequence of steps in the time domain. Let's examine what happens as a consequence of this in the frequency domain. Well, let's choose some type of simple representative spectrum. And of course, what's important about it is that the spectrum that we choose is band limited, or that there's an anti-aliasing filter. And it's not the shape, of course, that is critical. And as we work our way through the system, this is the continuous time spectrum. After sampling, that spectrum is replicated at multiples of the sampling frequency, integer multiples of the sampling frequency. And so there would be another one over here and another one over here, et cetera. And then in converting to a discrete time sequence, there is the associated frequency normalization so that the sampling frequency gets normalized to a frequency of 2 pi. Okay, now at that point, where we are in the system is at this point, so that we've converted to a sequence. We now want to carry out some filtering, and then after that filtering, convert back to a continuous time signal. All right, so here we are at the spectrum associated with the sequence. And now the processing that we're carrying out is linear time invariant filtering in the discrete time domain. And what that corresponds to then is multiplying this spectrum by the filter frequency response. And I've chosen a particular shape. And again, it's not the shape that's important to the discussion, but the fact, for example, that it has a particular cutoff frequency, which we'll kind of track as we work through this. And so now the spectrum of y of n, the output of the digital filter, is the product of this spectrum and the Fourier transform or frequency response of the digital filter. Now, in working our way through, we're going to take the output of the filter and undo the two-step process. So we now want to take that sequence, convert it to an impulse train, and then take that impulse train and desample through a low-pass filter. So here we are now at the output of the digital filter. We then convert that to an impulse train. Well, that's really undoing the original time normalization. And so what that means is that we are undoing the frequency normalization. In particular, we're dividing the frequency axis by capital T, whereas this point in y of omega was 2 pi. Now it's 2 pi over capital T. What that means is that equivalently, we're multiplying this spectrum by the frequency response of the digital filter, but now linearly scaled in frequency, so that what was a cutoff frequency of omega sub c is now a cutoff frequency of omega sub c divided by capital T. So now the next step in the process is the reconstructing low-pass filter, and what that extracts is simply the portion of this periodic spectrum around the origin. And so finally, then, the spectrum of the output of the overall system will be the spectrum of the input multiplied by a frequency response, which is the digital filter frequency response, frequency scaled by dividing that digital filter frequency axis by capital T. Okay, now what we can ask is we've got this processing, we've converted to discrete time, and we've gone back to continuous time, and one can ask now, what equivalent overall continuous time system does that correspond to? In other words, if that of course is a continuous time system, it's a continuous time input and continuous time output, and the overall system then would be one that would give us exactly the same output spectrum as we're getting. Well, what is that? What we have is an output spectrum, which is the product of the input spectrum and the digital filter frequency characteristic frequency scaled. And so, in fact, the resulting digital filter, continuous time filter, is simply the digital filter with an appropriate frequency scaling, in other words, with the frequency axis divided by capital T. So said another way, if we show here the frequency response of the original digital filter, then the corresponding continuous time filter would be this frequency scaled, and then because of the associated low-pass filtering in the reconstruction, we would select out just one of these periods, in particular the portion around the origin, and the essential consequence of that is that the corresponding continuous time filter then is given by this. And these two are related simply by a linear scaling of the frequency axis. And note that where the digital filter has a cutoff frequency of omega sub c, the continuous time filter has a cutoff frequency of omega sub c divided by capital T. So that's the linear frequency scaling. And by the way, plant away for now, and we'll return to this point later, plant away for now the observation that even if the digital filter frequency response is fixed, which we would assume it is, by changing the sampling frequency, in fact, what we're able to do is affect a linear scaling of the equivalent continuous time filter. Okay, well, this is pretty much the process and the analysis, but to highlight a number of the issues and emphasize these points, what I'd like to do is illustrate some of this with a videotape demonstration that, in fact, was made originally as part of another course, a course devoted entirely to digital signal processing, which essentially is discrete time processing, whether or not it's related to continuous time signals. And what I'd like to now focus on are some of the details of that demonstration. In the demonstration, the specific impulse response that is used for the digital filter or discrete time filter is the one that I show here. And the associated frequency response is the frequency response of a discrete time low-pass filter, as I indicate below. And the cutoff frequency of that filter, as I indicate, the filter was designed as a discrete time filter with a cutoff frequency of pi over 5. And let me just draw your attention to the fact that pi over 5 is also a tenth of 2 pi. And so, in fact, the digital or discrete time filter cutoff frequency is a tenth of 2 pi. And as I'll stress again shortly, remember that in the frequency normalization or unnormalization, 2 pi represents, in effect, the sampling frequency. And so the consequence of that is that the cutoff frequency really is going to be associated with a tenth of the sampling frequency. But for now, keep in mind that it's just simply a tenth of 2 pi. Now, the equivalent continuous time system in terms of the impulse response is, of course, a band-limited interpolation of the impulse response associated with the discrete time filter. And in the frequency domain, the frequency response is correspondingly a time-scaled and a frequency-scaled version of the frequency response. So, in fact, in the frequency domain and in the time domain related to the continuous time signal, the associated impulse response is what I indicate here, a band-limited interpolation of the discrete time impulse response and time-scaled, in fact. And the frequency response, following the discussion that we've previously gone through, is a frequency-scaled version of the one associated with the digital filter. Well, the first thing that I'll want to look at is the impulse response. And when we do, let me just indicate that in the actual implementation, things are slightly different than they are associated with the ideal analysis. In particular, in converting from a discrete time sequence to the continuous time signal, whereas this way of looking at it is convenient in the context of the analysis, in fact, the way it's done is using a more or less standard digital to analog converter. And what a digital to analog converter does, as I indicated in the previous lecture, is to convert the sequence not to an impulse train, but in fact to go directly through a zero-order hold. And so usually what comes out of a digital to analog converter is a staircase type of signal associated with a zero-order hold, and then the result of that is low-pass filtered to do the reconstruction. So what we'll want to look at then is that reconstruction first with just an impulse input. And so what we'll see after the low-pass filter for the impulse response is a smooth curve like this, but also as part of the demonstration, what I'll do just to show the zero-order hold is to take the low-pass filter out temporarily and then put it back in. So first, let's just look at the filter impulse response. What we see here is the impulse response of the overall system. And we observe, for one thing, that it's a symmetrical impulse response. In other words, corresponds to a linear phase filter. We can also look at the impulse response before the desampling low-pass filter. Let's take out the desampling low-pass filter slowly. And what we observe is basically the output of the digital to analog converter, which, of course, is a staircase or boxcar function, not an impulse train. In the real world, the output of a D-Day converter generally is a boxcar type of function. We can put the desampling filter back in now and notice that the effect of the desampling filter is basically to smooth out the rough edges in the boxcar output from the D-Day converter. Okay, so that's the impulse response of the system. Now what I'd like to show is the frequency response of the system. And to measure the frequency response, of course, what we can do is put a sine wave into the system and look at the sinusoidal output. So in particular now, what will happen is that with the system, we will put in a continuous time sinusoid, which is sampled, converted to a sequence. The sampled continuous time sinusoid is a discrete time sinusoid. That goes through the digital filter and gets attenuated or amplified appropriately. And then the output of that is converted back, and that's, again, a sinusoidal output. That gets converted back to a continuous time sinusoid, theoretically, as I indicate here, but again, as we just saw, really represented by a zero-order hold followed by a low-pass filter. So that's the overall operation, with one modification from the diagram that we have here. In this particular diagram, I've included an anti-aliasing filter. In fact, in the demonstration, there is no anti-aliasing filter. And so, in fact, the input is a sinusoidal input which is not band limited by virtue of an anti-aliasing filter. It's only, of course, band limited appropriately if we choose the sinusoidal frequency that way. So there is no anti-aliasing filter, and this is the system. And one consequence of that is that, in fact, if we sweep the input sinusoid only up to half the sampling frequency, we'll see no aliasing. But if we let it sweep past that, we're going to get aliasing. Now, in the demonstration, the sampling rate that's picked for this part of the demonstration is a 20 kilohertz sampling rate. That means, based on the sampling theorem, that as long as the input frequency is below 10 kilohertz, we get no aliasing. When the input frequency goes beyond 10 kilohertz, that higher frequency is going to get aliased down into a lower frequency. A consequence of that, then, is that as we go through the processing and we demonstrate the frequency response of the system, what we'll see in the output is no aliasing when the input is below 10 kilohertz. As the input sweeps past 10 kilohertz, when we let it, which we will eventually in the demonstration, then in fact that frequency, as it finally shows up here, will begin to be aliased down into a lower frequency. Another way of thinking about that is that when we watch the frequency response of the system, as we look at the digital filter frequency response, what we're sweeping as we go from 0 up to 10 kilohertz in the input frequency is this portion of the frequency response. As we sweep from 10 kilohertz out to 20 kilohertz, what we'll see is this portion of the frequency response. In other words, we'll see it periodically replicated. Or if we look at the corresponding continuous time frequency response, what it means really is that sweeping from 0 to 10 kilohertz is moving up this way, and then sweeping from 10 kilohertz to 20 kilohertz on the input, really because of the aliasing, reflects itself in the digital filter by looking back down toward lower frequencies, and so the continuous time filter sweeps back down from 10 kilohertz back to 0. Okay, so that's what we'll see, and we'll see it in several different ways as explained in the demonstration. So now let's look at the frequency response of the filter. Now what we'd like to illustrate is the frequency response of the equivalent continuous time filter, and we can do that by sweeping the filter with a sinusoidal input. So what we'll see in this demonstration is on the upper trace the input sinusoid, on the lower trace the output sinusoid, using a 20 kilohertz sampling rate and a sweep from 0 to 10 kilohertz, in other words, a sweep from 0 to effectively pi in terms of the digital filter. So we'll observe as the input frequency increases is that the output sinusoid will have essentially constant amplitude up to the cutoff frequency of the filter, and then approximately 0 amplitude past. So let's now sweep the filter frequency response. And there is the filter cutoff frequency. Now, we can also observe the filter frequency response in several other ways. One way in which we can observe it is by looking also at the amplitude of the output sinusoid as a function of frequency rather than as a function of time. And so we'll observe that on the left-hand scope, while on the right-hand scope we'll have the same trace that we just saw, namely two traces. The upper trace is the input sinusoid, the lower trace is the output sinusoid. And in addition to observing the frequency response, let's also listen to the output sinusoid and observe the attenuation in the output as we go from the filter pass band to the filter stop band. Again, a 20 kilohertz sampling rate and a sweep range from 0 to 10 kilohertz. Now, of course, we're in the filter stop band. Now, if we increase the sweep range from 10 kilohertz to 20 kilohertz, so that the sweep range is equal to the sampling frequency, in essence, that corresponds to sweeping out the digital filter from 0 to 2 pi, and in that case, we'll begin to see some of the periodicity in the digital filter frequency response. So let's do that now with a 20 kilohertz sampling rate and a sweep range of 0 to 20 kilohertz. And now as we come near 2 pi, we get back into the passband. And finally back to a 0 to 10 kilohertz sweep, so that we're again sweeping only from 0 to pi with regard to the digital filter. Now, an important observation is that with the digital or discrete time filter cutoff frequency fixed, as I've indicated here, and I remind you that what the cutoff frequency is 1/10 of 2 pi. With that cutoff frequency fixed, because of the normalization that we get as we come back to a continuous time filter, in fact, what we have is a cutoff frequency that is dependent on the sampling frequency or on the sampling period. And more specifically, since the discrete time or digital filter has a cutoff frequency which is 1/10 of 2 pi, the normalization, as you recall, is that 2 pi in discrete time frequency corresponds to omega sub s, the sampling frequency, in terms of continuous time frequency. The consequence is that this cutoff frequency, in fact, is 1/10 of not 2 pi now because of the normalization. It's 1/10 of the sampling frequency. So consequently, as we change the sampling frequency, what will happen is that even with the discrete time filter cutoff fixed, the cutoff frequency of the equivalent continuous time filter will change. Now, that's what I want to demonstrate, but let me again stress and ask you to keep in mind that this demonstration is done without an anti-aliasing filter in, and we are going to be changing the sampling frequency. And so keep in mind that as we look at this, as the input frequency sweeps past half the sampling frequency, whatever sampling frequency we happen to be looking at, then because of the fact that there's no anti-aliasing filter, we'll get aliasing. In other words, the frequency in the digital filter or discrete time filter, as we sweep the input frequency up, will move up in frequency until we get past half the sampling frequency, and then essentially we'll move back down in frequency. Consequently, what we'll get then are, or what we'll see, are periodic replications of the frequency response when we swept past half the sampling frequency. All right, so now let's look at the same digital filter, but the frequency response as we change the sampling frequency. Now what we would like to demonstrate is the effect of changing the sampling frequency. And we know that the effective filter cutoff frequency is tied to the sampling frequency, and for this particular filter corresponds to 1/10 of the sampling frequency. Consequently, if we double the sampling frequency, we should double the effective filter passband width or double the filter cutoff frequency. And so let's do that now. Again, a 0 to 10 kilohertz sweep range, but a 40 kilohertz sampling frequency. And we should observe that the filter cutoff frequency has now doubled out to 4 kilohertz. Now let's begin to decrease the filter sampling frequency. So from 40, let's change the sampling frequency to 20 kilohertz. We should see the cutoff frequency cut in half. Now we can go even further. We can cut the sampling frequency down to 10 kilohertz. And remember that the sweep range is 0 to 10 kilohertz. So now we'll be sweeping from 0 to 2 pi. So as we get close to 2 pi, we'll see the passband again. And now let's cut down the sampling frequency even further to 5 kilohertz. Here we are at 2 pi. And then at 4 pi. All right, so that illustrates the effect of changing the sampling frequency. Now let's conclude this demonstration of the effect of the sampling frequency on the filter cutoff frequency by carrying out some filtering on some live audio. What we'll watch in this case is the output audio waveform as a function of time on the single trace scope, and also we'll listen to the output. We'll begin it with a 40 kilohertz sampling rate, then reduce that to 20 kilohertz, 10 kilohertz, and then 5 kilohertz. And in each of those cases, the effective filter cutoff frequency then is cut in half from 4 kilohertz to 2 kilohertz to 1 kilohertz, and then to 500 cycles. So let's begin with a 40 kilohertz sampling frequency, or an effective filter cutoff frequency of 4 kilohertz. Now let's reduce that to a 20 kilohertz sampling frequency, or a 2 kilohertz filter. Then a 10 kilohertz sampling frequency. And finally, a 5 kilohertz sampling frequency corresponding to a 500 cycle equivalent analog filter. All right, now let's finally conclude by returning to a little higher quality ragtime by changing the sampling frequency back to 40 kilohertz. All right, well, hopefully what you've seen in the demonstration and in this lecture gives you a sense and a feeling for the analysis and the use of discrete time filters for processing continuous time signals. And as you may be aware, and as I've tried to indicate previously in the past, this in fact is one very important, but not the only, but one very important context in which discrete time filtering is used. And this in fact is an area that is developing rapidly because of the fact that microprocessors, digital technology, computers, etc., afford considerable flexibility in carrying out digital processing of signals. And when digital processing is used, that naturally corresponds to implementing the processing and analyzing it in discrete time. Now, in the next lecture, we'll be continuing on another aspect, developing another aspect of sampling. And in particular, what we'll be talking about is sampling of discrete time signals. As I'll indicate there, one of the contexts in which discrete time sampling, in fact, plays an important role is in the context in which we are processing continuous time signals using discrete time processing, where, in fact, one step that we might want to take in addition to the steps that we've talked about here is an additional sampling process following whatever kinds of filtering that we do. Well, that's a discussion and a topic that we'll be going into in the next lecture. Thank you.